This CFD training package is prepared for intermediate users of ANSYS Fluent software in the Turbomachinery area. You will learn and obtain comprehensive training on how to simulate projects. This package consists of three main parts: introduction of turbomachines and their application, introducing CFD methods in simulating turbomachines, and 10 training videos simulating turbomachines in Fluent software. And this video is related to the third part. By clicking on the subscribe button, you will be informed about the newest CFD training videos by MR-CFD. Or if you are watching the training video, click on the MR-CFD logo and subscribe. To teaching the basics of turbomachines and CFD simulation models for them, 3 simulation training examples by ANSYS Fluent software are included for you in this package. These are Liam F1 wind turbine, 3-blade horizontal axis wind turbine, vertical axis wind turbine, Darius wind turbine evaluation, helical wind turbine, water wheel or Pelton wheel, Francis turbine, Kaplan turbine, axial flow compressor, and FSI method for water turbine. The simulation training examples included in this package are among the most famous examples of turbomachine simulations. This project is going to simulate an airflow field adjacent to Liam F1 wind turbine by ANSYS Fluent software.
If display mesh button is selected, the Fluent software allows us to display each surface of our computational domain individually, and also there are various options given for us to select the colors, to observe the edge of the meshes, and even our mesh nodes if such needed arise. So, as we've discussed, even though we are not going to simulate a porous zone or a laminar zone or other materials for our current problem, however, we're going to need to specify the rotating geometry. So what we're going to do is to go to the zone corresponding to the rotating geometry, that is the yellow zone depicted in the slides. What we're going to do is to select the frame motion so that we're implying that this zone is going to have a motion. And what the motion would be a rotational motion that we're going to define its axis and its center, and more importantly, the RPM corresponding to its rotation. And afterwards, the solver would definitely know and understand how to define the forces corresponding to this rotation. It's really important to know that the frame motion does not really rotate our geometry. However, it is going to inflict the two forces known as Coriolis and centripetal force that would be generated due to the rotation of this wind turbine. So by doing so, we are going to get away from a transient simulation that mesh motion implies and significantly reduce our computational resources while achieving an acceptable accuracy. Also, for our stationary zone, that is the zone corresponding to the big rectangular zone, there is no need to adjust any other setup for the current simulation. Finally, regarding the choice of our discretized variables, we must always end the solution with a second order accurate discretization. Why? Because our equations themselves have been defined by second order derivatives. So a first order derivation and a first order approximation would lead to a highly dispersed result. However, if we start our solution with a second order accuracy, we're going to confront numerical instability and convergence difficulties. So as a solution, it's better to start our simulation with a first order accurate discretization, and after partial convergence has been observed, we could go back and switch the discretizations to a second order accurate. Also, one can select both coupled procedures or segregated procedures for the pressure velocity treatment. But as a tip, user must always remember that coupled treatment of velocity and pressure would lead to better convergence. However, it significantly increases the solution time as the mesh counts increases. However, in general aerodynamic or turbomachinery CFD investigations, the velocity magnitudes and the velocity contours are the most informative contours regarding the behavior of the fluid flow adjacent to our interested zone. In this project, the Liam turbine surface, which is located inside the rotation zone, has the highest velocity gradients, and the wicks behind the rotating zone could be easily observed through the velocity contour.
In this project, we are going to simulate the three-blade horizontal axis wind turbine. Actually, the present study deals with airflow on the HAWT blades, so that the purpose of the problem is to study the distribution of velocity and pressure on the surfaces of the blades and on their body.
The present study deals with the airflow on the HAWT blades, so that the purpose of the problem is to study the distribution of velocity and pressure on the surface of the blades and on their body. There are three areas around the blades for airflow. There is an area around the blades, an area in front of the blades, an area behind the blades. The airflow behaves normally in front and behind the blades, while in the area around the blades, the rotational motion of the blades causes the rotational airflow. Now, if you double click on each of the two zones shown here, in the appeared window you will see air is set in front of the material name. Now, if you double click on the moving zone button in the appeared window, you will see we have also enabled the frame motion option. After enabling that option, a new part will appear under the reference frame tab. In this section, all you have to do is to change your rotational velocity section and set the speed equal to 72 radian per second. Next, if you double click on the boundary conditions button and then click on inlet boundary, you will see the type of this boundary is defined as velocity inlet. By clicking on edit button, a new window will appear in which you can change the settings for this boundary. In this window, you will see a moment coefficient report output type is defined over the wind turbine walls. Now, in order to extract the velocity vectors, you have to click on vectors button and then accept the appeared window. And finally, in this slide, you can clearly see the velocity vectors of the airflow and how they rotate around the blade. Finally, a summary of the settings and setup that we have used in our project is presented in this slide.
Project 3 simulates the airflow passing over an H-type Darius wind turbine. Its results are compared and validated with the results in the article in this project.
The present problem simulates the airflow passing over an H-type Darius wind turbine. The simulation is based on a reference paper named Wind Tunnel and Numerical Study of a Small Vertical Axis Wind Turbine, and its results are compared and validated with the results in the article. In this project, the airflow enters the computational domain with a velocity of 5.07 meter per second, and the RNG-K epsilon model is exploited to solve the turbulent flow equations as the paper stated. Also, it should be noted that the mesh motion option was enabled to simulate the rotating motion of turbine blades. Also, by clicking on report quality, again in the console tab, the Fluent software will give you the quality report for your mesh. For example, you can see the maximum aspect ratio of your mesh, maximum orthogonal quality, and etc. Next, if you click on the outlet boundary, you can see that the type of this boundary is defined as pressure outlet. Now, just like the previous boundary, if you click on the edit button, you can further adjust the settings related to this boundary. In the appeared window, under the mesh interfaces section, if you click on each of these interfaces, you can see the two interfaces that are placed over each other and are related. After double-clicking on the residuals button, a new window will appear. In the appeared window, you can see the absolute criteria for equations like continuity, x velocity, y velocity, and so on. Now, when you set the software to start the simulation, there would be error between each iteration. Now, if that error is less than these criterion, it conveys the meaning that that equation has reached convergence. In the appeared window under the contours of section, we select velocity as our desired variable, and then under the surfaces section, we select our previously defined plane. And now in this slide, you can easily see the velocity distribution inside our computational domain when the airflow passes over the blades of our turbine. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
Project 4 is going to simulate an airflow field close to a vertical axis Darius wind turbine.
Also, important setups such as solver type must be selected in the General tab. While pressure-based solvers are usually employed for most CFD simulations, the density-based solvers could be selected if a compressible gas with a Mach number above 2 is the objective of the study. Also, the user must specify if the simulation is steady state or transient. Finally, it has been allowed to select the gravitational acceleration and specify both value and direction in the General tab for the user to complete. However, the user could change the gravitational acceleration in the Operation tab inside the Boundary Condition section. As a good practice, it is advised to start the transient simulation with a previous steady state simulation which is converged with a situation close to our transient simulation. For this specific simulation, what we could do to simplify our convergence, we could start with a steady state frame motion setup, and after we've reached a satisfiable partial convergence, we could just copy our frame motion simulation to a mesh motion simulation using the copy option inside the cell zone. And by doing so, the ANSYS Fluent software would automatically switch from steady state solver to transient solver without posing any additional setups. To do so, we simply right-click on the report definition and select the drag out of the options. Afterwards, what we're going to do is to select the wall that we want to calculate the drag on it and the direction of the flow that encounters the wall that we want to calculate the drag. We could also specify to write these values into the files or to plot the values during the solution. Also, an interested user could dive in and see the options and parameters that the report definitions could deliver during the iterations. So that is all, and I hope you've enjoyed this simulation and understand the basis of the aerodynamic and turbomachinery simulations. To further simplify the setups, a brief guideline of the settings that we've been through in this study is presented in the below table, and I hope you would recreate this geometry or the simplified version of this geometry and carry out the simulation that has been discussed here and have an awesome CFD experience. Thank you for your attention and good luck.
This project is going to simulate an airflow field close to a vertical axis helical wind turbine.
Depicted in the following slides, the geometry of interest has been discretized into numerous mesh elements which will consist of tetrahedral elements for the core of our domain, while we've used prism layers for the boundaries in which the boundary layer would be formed. In our cell zone tab, what we're going to do is that we're going to the rotary zone, which is the inner cylindrical zone, and we're going to select the mesh motion condition. Afterwards, we're going to give our mesh motion or our rotary zone a specific angular velocity, an axis for rotation, and also a single point as an origin for our rotation axis. So, by doing these setups, the computer or our solver would understand how to rotate our body, and by rotating our rotary zone, we're going to observe how the airflow is going to vary due to this rotation. And afterwards, we're going to check that right material is associated to our rotary zone, and also right material is associated for our stationary zone. And for our stationary zone, there are no more setups to check for this simulation. As a good practice, it is advised to start the transient simulation with a previous steady state simulation, which is converged with a situation close to our transient simulation. For this specific simulation, what we could do to simplify our convergence, we could start with a steady state frame motion setup, and after we've reached a satisfiable partial convergence, we could just copy our frame motion simulation to a mesh motion simulation using the copy option inside the cell zone. And by doing so, the ANSYS Fluent software would automatically switch from steady state solver to transient solver without posing any additional setups. By applying a valid boundary condition, the problem has been defined fully for the software to begin the simulations. However, the software still needs to know how to solve the discretized equation. And in order to give those information to the software, the method options must be selected appropriately. To visualize our variables in different locations, we first need to create the plane on that location. To generate a plane, what we're going to do is to go to the surface panel, we right click on the surface panel and click on create a plane, and we create our desired plane. After we've created our desired plane, we could visualize our variables such as velocity magnitude or pressure on that plane. So in this study, we visualized our velocity magnitude in the plane in the middle of our domain, and we've adjusted the minimum and maximum values of our variable to improve our visualization of our problem. Afterwards, we've visualized our pressure contour on our blades wall, which is very informative about the sensitivity of our blade regarding the pressure drag. Other parameters such as vorticity magnitude or Y plus could be further studied through our contour variables. Also in this study, we've demonstrated flow movement through the use of vectors, which is pretty informative to understand how our wind turbine guides the flow pattern. So that is all, and I hope you've enjoyed this simulation and understand the basis of the aerodynamic and turbomachinery simulations. To further simplify the setups, a brief guideline of the settings that we've been through in this study is presented in the below table, and I hope you would recreate this geometry or the simplified version of this geometry and carried out the simulation that has been discussed here and have an awesome CFD experience. Thank you for your attention and good luck.
In this project, we simulated the water wheel by ANSYS Fluent software.
The geometry of turbine is designed by SolidWorks software and divided into a smaller section to improve the geometry and mesh of the turbine. The geometry is divided into two general sections of rotary and stationary section. The rotor part consists of a turbine and the cylinder that is located around the turbine, and the stationary part actually surrounds the rotatory cylinder. After double-clicking on Multiphase button, a new window will appear. Under the model section, you can see that volume of fluid model is activated. Also, the number of Eulerian phases used in this project is equal to 2. And under the VOF submodels, open channel flow is activated since we wanted to simulate the interaction of two phases of air and water. The body force formulation is activated and implicit body force is used since we wanted to see the impact and effect of gravity on each phase. By clicking on Phases tab, In order to define an algorithm to solve the fluid flow, we double-click on the viscous button and a new window will appear. In the appear window, you can see that RNG-K epsilon model is activated. We have chosen RNG-K epsilon over the standard form because the RNG is more accurate and gives us better result than the standard format of K epsilon. Now, by clicking on the first report, which is a momentum report, you can see that the software will automatically calculate the momentum of phases on zones and surfaces like leading edge and water wheel. Actually, you can add this report by clicking on new and then going on to the force report and then clicking on momentum report. Now, in order to define and extract the contour, just have to right click on the contours and then click on new. In the appeared window, under the contours of section, for example, we click on pressure. And since we made and defined a new plane in the previous slides and we want to show our contour on that plane, under the surfaces section, we click on plane 17 and then click on save and display. In the presented contour, you can easily see the increased pressure on the tip of the blades where the water flow touches the turbine. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
The present problem simulates the water flow inside the ANSYS weather turbine.
The meshing of the model has been done using ANSYS meshing software and the mesh type is unstructured. The element number is equal to 4,653,160. Also, the quality of the mesh is considered finer in the areas close to the blades. Now, in this project, there are several assumptions taken into account. The first assumption is that the type of our solver is set to be in pressure-based format since we are dealing with incompressible flows. Also, the velocity formulation is taken to be in absolute form. And as for the time study, we have selected the steady time study since we don't want our results to be a function of time. Also, the gravity is activated and its value is equal to minus 9.81 in z direction. Under the phases tab, you can see that two phases of water and vapor are defined. In order to add a phase, you just have to click on the Add Phase button. However, it should be pointed out that you need to first define the material before adding a new phase. Adding a new material will be explained in the next slides in the material section. Now, in order to define a new material, just have to right-click on the fluid and then select the new. After selecting the new, a new window will appear. In the appeared window, you either can define a new material by defining its properties yourself, or you can click on Fluent Database and select a material from the available list. However, by clicking on Vol Moving Zone, you can see that the vol motion defined for its boundary is set to be moving vol. After clicking on Volume Rendering button and accepting the appear window, in the low left side of the software window, you can see that a new setting will appear. In the appeared setting, in front of the variable, for example, you want to see the pressure contour. You just have to select the pressure variable from the available list and then click on Apply to see the 3D contours of pressure. Now, in order to see the streamlines, you just have to click on the Streamline button and accept the appeared window. Again, on the low left side of the software window, in front of the Start From section, you just have to select the inlet boundary so that the software will calculate the streamlines entering the computational domain from this boundary. After that, just have to click Apply so that the software will show you the streamlines. In the streamlines contour, you can easily see how the streamlines have moved inside the rotating domain. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
Project 8 is going to simulate the water flow passing over the Kaplan turbine.
The mesh type used for this geometry is unstructured and the element number is 919,000 824. Now the next step is to define the rotating zone or the frame motion to our domain. To do that, we expand the cell zone condition and then go under the fluid and double click on the fluid. After that, in the appeared window in front of the material name, we first have to select the water liquid material, and beneath it we enable the frame motion. After that, we go under the rotational velocity section and we set the value of the speed to be equal to 3300. And for this wall, you can see that we have selected the stationary wall motion along with no slip shear condition. After double clicking on the method, you will see that a new window will appear showing you the pressure velocity coupling. Also, you can see that the spatial discretization methods are shown in this window. Also, you can change this discretization into other formats, like you can change them into first order advent and the other options available for each variable under their combo list. And for the simple pressure velocity coupling, the simple algorithm is kind of an iterative solver which uses a relationship between velocity and pressure corrections to enforce mass conservation and to obtain the pressure field. Now in order to extract a 3D contour, we click on volume rendering button and accept the appeared window. After that, on the low left side of the software window in front of the variable section, we select our desired variable, which in this slide we are going to select the velocity. After that, we click on the apply button and the software will show us this 3D contour. Now in this slide, you can see the velocity distribution inside our computational domain. And finally, in this slide, you can see the velocity distribution on a plane, which is placed in the middle section of our geometry. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
In this project, axial flow compressor is investigated.
The meshing of the present model is done using ANSYS meshing software. The mesh type is unstructured and the element number is 278,162. The size of the grid in the area adjacent to the blade is smaller and more accurate. In this window, you may be able to choose different units for different quantities. For example, you can choose different units for acceleration, for angle, angular velocity, and so on. But you left these quantities without changes. Just click on the close button. In the appear dialog box, we enable the energy equation, since we are dealing with the compressible flows and that we want to know the temperature distribution alongside the compressor blades. Energy equation is an equation which couples the velocity of the flows to the temperature of it. After clicking on the edit button, you will see that a new dialog box will appear just like before. The settings in this dialog box are like the last dialog box, but the two different. The first difference is that the radial equilibrium pressure distribution is activated, and the second difference is that the target mass flow rate is also activated. The target mass flow rate is set to be equal to 33.25, and also upper and lower limits for absolute pressure is also defined. You may also define turbulence specification in this dialog box too. After double-clicking on the control button, a new window will appear showing you different values for current number and under relaxation factors. Here in this project, the current number is set to be equal to 0.2. For problems with high nonlinearities, the current number should be set to near 0. And as the simulation process progresses, we may change the current number into higher values. In the pressure contour, we can see that in the starting point of the blade, the pressure value is much more than the pressure of the value at the ending point of the blade. Since, by the rotation of compressor blades, the airflow will gain more velocity through the rotating frame, the pressure will drop. Finally, in the velocity vector contours, you can see the vectors of velocity and the direction the airflow moves. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide alongside the ideal gas equation, which is our main equation, and we have based our premises and assumption on this equation.
Project 10 investigates the water flow around a vertical water turbine considering a steady CFD simulation.
The present 3D model was designed by Design Modeler software. The geometry of the model consists of a large cubic space as a fluid domain and a water turbine inside this space as the solid domain. Now, after defining the water-liquid material under the fluid under the cells and conditions section, all we have to do is to change the material name to water-liquid. Now, after double-clicking on the dynamic mesh option in the appeared part, you can see that we have enabled the dynamic mesh option, and underneath it, in the mesh method section, you can see that we have enabled two options of the smoothing and remeshing. Now, to further change and modify these options, we click on Settings button. In the appeared window under the Smoothing tab, you can see that we have selected the Spring Laplace Boundary layer. Now, smoothing is an option that we use in order to increase the quality of distorted mesh after each remeshing interval. In order to further change the settings for this method, we click on Advanced button. Now, in the workbench environment, we click on Transient Structural and drag it next to the Fluent software block in order to add the mechanical liquidial software. After that, we click on System Couplings and also drag it next to the Transient Structural block in order to couple these two softwares. Now, in the appeared window, all we have to do is to define a mutual relation between the Fluent software and the mechanical liquidial software. To do that, we right-click on Data Transfer and then select Create Data Transfer. After that, on the low left side of the software window, in front of the location, we select our blade, which is the solid object, and in front of the variable, we select pressure as our desired variable. After that, we click on Apply, and the software will show us the pressure distribution on the solid object or the blade. Now, in this slide, you can easily see the pressure distribution on the surface of the solid object, which is also known as the blade. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
To have the complete explanations, obtain the full training movies by purchasing this product. To benefit from MR-CFD services including simulation, consultation, and training, contact our experts via info@mr-cfd.com, www.mr-cfd.com.